Good morning, students. Today we will discuss the first module of strength of materials, which covers simple stress and strain. So, all of you know about forces, moments, all those things. In your mechanics, you have studied that. A force is an external agent which tries to change the equilibrium or the state of equilibrium of a body. So, whenever a force acts on a body, some deformation takes place. So, all those things you have learned. If the deformation is very small, then you can neglect it and that body is called as rigid body. If you have to consider the deformation, then it is called as elastic body or deformable body. So, in strength of materials, we deal with deformable bodies wherein we find the stresses, strains induced in a particular body subjected to some external force. So, the difference between pressure and stress is an internal effect. So, when some external force is acting on an object, there develops an internal resistance. So, that internal resistance developed by the body is known as stress. Of course, its unit is expressed per unit area. So, force per unit area only, it is the unit of stress, which is nothing but Newton per millimeter square. Pressure is also expressed in the same units, only thing is it is expressed in pascals. So, Newton per meter square. So, pressure is an external effect, stress is an internal effect. Now, in strength of materials, we deal with different types of strengths of materials. So, today we will take up only these two, tensile strength and compressive strength. So, tensile strength means when a material is subjected to tension force. So, P like this. So, we can call it as pull force. Pull force. P is the tensile force. This is the material. Length of the specimen of that material is L. When it is subjected to a pull force P, naturally the tendency is to get elongated. That means the length will increase. So, I will take the new length as L plus delta L. Once the length is increased, the cross sectional area A, which I have taken here, the cross section can be anything. It can be circular, it can be rectangular, square, anything. The cross sectional area reduces. So, when length increases, cross sectional area reduces. So, here delta L is, I will call it as elongation because there is a stretch, there is an increase in length. This is your new length. So, the difference is the change in length, or it is called as elongation. That elongation is given by this formula. Delta L is equal to PL by AE, where P is the tensile force acting on the specimen over the cross sectional area A. Length of the specimen is L. E is an elastic constant which is known as Young's modulus of the material or modulus of elasticity, which depends on the type of material. Of course, this derivation I have given in the lecture notes also and in the video class also. You can see to that. Now, here stress, as already told, it is the ratio of the internal resistance force to the cross sectional area. Normally it is expressed in Newton per millimeter square. N is the internal force developed, the millimeter square is the area. So, this is also denoted by MPa. MPa means megapascals. So, 1 pascal is 1 Newton per meter square, 1 megapascal is 1 Newton per millimeter square. So, whatever stress that develops due to tension force, that is called as tensile stress. Then we can just denote it as sigma T. So, sigma stands for the stress, T stands for the tension. So, P by A. Similarly, we are going to define another term called strain. So, since tensile stress develops within the body, tensile strain will develop. So, that is epsilon T. Epsilon is strain, T stands for tension. Epsilon T is given by change in length divided by initial length. So, here change in length is elongation, delta M by L. This has no units, because both are expressed in the same units. Millimeter by millimeter, it cancels. In some books, they use millimeter by millimeter also, but anyway, it is unitless or dimensionless, whereas stress has the unit of Newton per mm square. This is regarding tensile stress. The another type of stress is compressive stress. So, when you apply push force like this on both the sides of the specimen, then reverse effect will take place. That means length will reduce, initial length is L, it reduces by delta M. So, length will reduce but area will increase. So, area increases, length reduces. This increase in area, you can take it as A plus delta A plus delta A. So delta A is the increase in the area. Now here this delta L we call it as contraction. That is the decrease in length. Contraction is decrease in length. Elongation is increase in length. So that is the word we are going to use. Once again, the formula remains same for calculating this decrease in length or contraction. PL by AE. Only difference is P is the compressive force applied here. A is the cross sectional area of the member. So if it is a circular cross section, it is pi d square by 4. If it is rectangular cross section, it is width into depth. It is a square cross section, it is side square. So depending on the cross section, so we have to decide the area. So a suitable formula we have to use, and we have to take up the respective formula for the area. It can be rectangle, it can be circle or square like that. So you will be knowing the diameter, you can find out the area by pi d square by 4. Here you will be knowing the width and the depth, so you can calculate the area. So once you know that the area, so sigma is stress, C stands for compressive stress. Once again it is P by A, expressed as usual in Newton per mm square and MPa, and compressive strain, whatever develops within that, that is epsilon is strain, C stands for compressive strain, and delta L by L. So same formula, here also it is unitless because millimeter per millimeter. That means normally in this chapter we discuss about tensile strength, compressive strength, or tensile stress and compressive stress, and these two are called as direct stress. Direct stress or normal stress, because these stresses they develop at right angles to the cross section area. So this is the cross section area. When you cut the specimen like this perpendicular to the board, you are going to get the cross section area like this. This is the cross section area. This area is A, or this area is B if it is rectangular. Okay, once you know area and the force, you can calculate the stress developed within that. So, and normally in doing problems, while doing problems, we take elongation as positive and contraction as negative, because if you take multiple stepped bars like this, so problems of this kind, if you have some 3 or 4 bars together, some bars may be subjected to tension, some bars may be subjected to compression like this. For example, this bar 1 is subjected to compression, bar 3 is subjected to tension. Okay, this is tension, this is compression. In such a case, some bars, some segments may be subjected to tension, stress, some bars will be subjected to compressive stress. So while you are, and finally you are interested in finding the total elongation, that is delta L. So delta L1 is the elongation or contraction in this portion, delta L2 is in this portion, delta L3 is in this portion, and your total elongation will be delta L, which is summation of delta Li, that is delta L1 plus delta L2 plus delta L3, out of which if it is compression, for example here, first bar is subjected to compression, your delta L1 will be negative, and here tension, this is positive. But in the middle bar, depending on the forces, magnitudes, we have to decide whether this middle bar is subjected to tension or compression. Based on that, we have to take it as positive or negative. So this is how. So we are going to discuss in the next class. We are going to discuss some problems on this. What we call it? These are called as stepped bars. So in stepped bars, you have different cross-section areas. Area of this is different. A1 is the area of this. A2 is the area of this. A3 is the area of this. And lengths also will be different. L1 is the length of this. L2 is the length of this. L3 is the length of this. Whereas Young's modulus value, it remains same if it is consisting of same material. So E value remains same. So using this formula, PL by AE. So P you will be knowing. So whatever force acts on this, that is P1 you can take. Force acting on this is P2. Force acting on this is P3. Then L1, L2, L3 we have to take for this. Then A1, A2, A3 they are the areas of these three. Then Young's modulus remains same provided if all the three segments are of the same material. So in the next class we will discuss about how to find the total deformation delta L of a stepped bar. Okay, thank you.